Hello, everyone, and welcome to the Science of Childhood Cancer lecture series hosted by the St. Jude Comprehensive Cancer Center. My name is Alberto Papo, and I'm the head of the Division of Solid Tumors and the co-leader of the Developmental Biology and Solid Tumor Program at St. Jude Children's Research Hospital. It's my pleasure today to welcome Dr. Crystal Mackel from Stanford University. Before I introduce her, I'd like to briefly mention that you can submit questions at any time during the talk using the chat function and sending questions to all panelists. All questions will be answered at the end of Dr. Mackel's lecture. Or if you need help sending the questions, you can email them at soc@stjude.org. If you experience any technical issues during the talk, please contact soccsupport@stjude.org. Dr. Crystal Mackel will leave time for questions before the top of the hour and has also kindly offered to stay on for additional time after the close of the official event if anyone would like to stay for further discussion. And now I am delighted to introduce our speaker, Dr. Crystal Mackel, who is the Ernest and Amelia Gallo Family Professor and Professor of Pediatrics and Internal Medicine at Stanford University. Dr. Mackel is also the founding director of the Stanford Center for Cancer Therapy and serves as the Associate Director of the Stanford Cancer Institute, leads the Cancer Immunology and Immunotherapy Program, and is the Director of the Parker Institute for Cancer Immunotherapy at Stanford University. Dr. Mackel is an international recognized translational researcher whose program focuses on immuno-oncology. Dr. Mackel obtained her medical degree at Northwestern Ohio University in Rootstown, Ohio. This was followed by a combined pediatric and internal medicine residency at the Children's Hospital of Akron and a fellowship in the pediatric oncology at the pediatric branch at the NIH in Bethesda, Maryland. During her 26 years at the NIH, she became the head of the immunology section of the pediatric oncology branch and ultimately the chief of the pediatric oncology branch at the NCI. Dr. Mackel was instrumental in identifying the essential role of IL-7 as a master regulator of T-cell homeostasis and has conducted multiple first in-human and in-child clinical trials that comprise a wide range of novel therapeutic interventions, including peptide vaccinations with IL-2 on autologous cells, administration of subcutaneous IL-7, pulsed dendritic cell vaccines, genetically engineered NY-ESO-specific T cells for patients with synovial sarcoma, autologous NK cells with IL-15 in pediatric solid tumors, as well as a variety of CAR T cells with GD2, CD19, and CD22. More recently, Dr. Mackel chaired the Children's Oncology Group trial with ipilimumab and nivolumab, which is the largest immune checkpoint inhibitor trial ever conducted in the United States. Dr. Mackel has been an extraordinary mentor to numerous fellows and doctoral students who have successfully transitioned to prominent roles both in academia and pharma. She has served in multiple advisory committees and consulting grant reviews and has been the recipient of numerous research grants, which more recently include the California Institute of Regenerative Medicine to study the use of bispecific CD19 and 22 CAR T cells in adult B-cell malignancies, as well as a U54 grant, which is co-led by her and Dr. Maris to discover new immunotherapeutic strategies for childhood cancer, and a Stand Up to Cancer grant also co-led with Dr. Maris to use genomics to exploit immunotherapeutic targets in high-risk pediatric tumors. Dr. Mackel is a prolific writer with over 140 peer-reviewed manuscripts and 90 invited manuscripts and book chapters. Dr. Mackel is a member of the American Society of Clinical Investigation, the American Academy of Physicians, and received the Lila and Murray Gruber Award for Cancer Research in 2019. She serves on numerous national leadership positions, including co-PI of the NCI Pediatric Cancer Immunotherapy Network, leader of the NCI Pediatric Cancer Immunotherapy Trials Network, and co-leader of the St. Baldrick's Stand Up to Cancer Pediatric Dream Team. Crystal, we are thrilled that you accept our invitation to participate in the Science of Childhood Cancer lecture series and look forward to your presentation entitled CAR T Cell for Pediatric Cancers, Progress and Challenges.
Wow, thank you, Alberto. That was really comprehensive. Thank you so much. All right, thank you for the very kind introduction and for the invitation to present in this, looks like a great venue. It looks like it was going up over 200 people. So thanks everyone for making the time. So these are some disclosures. In my business with CAR Ts, there are a lot of companies, and I have consulted for several and have received these patent royalties for our CD22 CAR and spun out a couple companies. So childhood cancer, you know, I don't think I have to tell this audience, this is why you all are watching, is you understand that despite all of the progress, it's still a major problem. About 12,000 new cases per year in the US, remains the leading cause of death due to disease after infancy in childhood. We don't really know the numbers worldwide, but more than 150,000. And while the cure rates, you know, are really much, much higher than they were 50 years ago when the field of oncology became a real entity, there's still perhaps about 20% of children that we lose. And those children who are cured oftentimes trade one disease for another because the cures come through the use of very intensive and toxic therapy. And these have alarming rates of late effects. Chemotherapy, which is the backbone of nearly all curative regimens for pediatric cancers, can only take us so far because oftentimes these cancers develop resistance to chemotherapy that tends to extend beyond the chemotherapeutic agents they've received. And so this whole problem of chemoresistance has resulted really in plateaus in survival over the last 20 years or so. And there's been so much advance in terms of understanding what drives these cancers. And has given rise, this advance has given rise to some molecularly targeted therapies, but still, because of the nature of the biological mechanisms at play, these are largely transcriptomic and epigenetic aberrancies in our childhood cancers. This means that those small molecules that are largely focused on kinase inhibition remain only a minor part of our armamentarium. And there still are some diseases for which, we make a diagnosis and we tell the family that there really isn't much we can do beyond standard therapy, but we know that, the vast majority of these children are going to pass of their disease. Examples being DIPG and ATRT. And this is really the picture of the problem of disease recurrence, because we really get, for the most part, a chance to cure cancer the first time around. And if we don't do that, our ability to cure the recurrent disease in these patients becomes much less effective. Now, acute lymphoblastic leukemia, of course, where there have been great strides, but in the setting of acute lymphoblastic leukemia, even refractory disease has been, largely lethal. And this is where hopefully I'll tell you some news today around CAR T cells, where I think that is changing a bit. But as Alberto alluded to, when you ask about immunotherapy to most physicians in the world and even to the lay public, what you hear about is that, yes, it's been a revolution, but it's largely been driven by immune checkpoint blockade. And immune checkpoint blockade is a very, elegantly simple idea that we came to understand that for a lot of cancers, the immune system has already recognized the tumor and has weapons that can be used against the tumor if only we can inhibit a suppressive signal that the tumor is providing to allow the tumor to escape. So in other words, if we can just take off the brakes, there's an immune response underneath the surface. And this elegantly simple concept really was recognized by the Nobel Committee in 2018, and Jim Allison and Takira Hanjo received the Nobel Prize for this work. And by all measures, it indeed has been a revolution in cancer medicine. But that poses the question, what about childhood cancers? And we undertook the first trial of an immune checkpoint inhibitor at the NCI, ipilimumab. And at the time, it was interesting. We had trouble accruing to this trial because it was before people really thought checkpoint inhibition was important, certainly in the pediatric space. We enrolled 30 children, and we went pretty high on the dose because at that time we thought that Bristol Myers was going to get an approval for their higher dose. It ended up, they settled on the lower dose. But what we learned at that high dose was that these children often developed autoimmunity and inflammatory toxicity that was really quite severe. And despite all of that, we saw very little in the way of responses. We enrolled 11 children with metastatic melanoma, of course, very rare in childhood, but we enrolled them because that's where this agent had the most clear activity in adults. But we didn't see any responses in children's melanoma. And we also enrolled some sporadic, more common pediatric solid tumors. Again, no objective responses. And now, in the patients who had the autoimmune toxicities, it appeared that perhaps they had some prolongation in survival, and that's shown here in this curve. But it still was nothing that was, definitive, and simply not good enough given the toxicity that we were observing. Now, of course, nivolumab or the PD-L1 axis blockers are the kinder, gentler forms of immune checkpoint inhibitors. And it took us a long time to get these trials launched in childhood, which is a darn shame and is really reflective of other challenges related to drug development in children. But once we finally got them launched, there were really 3 trials happening simultaneously. Nivolumab in the US, and that's the one that we led as part of the Children's Oncology Group Phase 1 consortium. And then there were 2 that were happening mostly in Europe. One is pembrolizumab and the atezolizumab, the anti-PD-L1 from Genentech and Roche. And, the bottom line is these all came out in publication form this year, was that the findings were remarkably similar across all of these. And that is that there were some responses in lymphomas, but the responses in sporadic pediatric solid tumors were essentially absent. The largest trial with Pembro did see a response rate in about 5%, but they enrolled 136 of these patients, and the vast majority of these children did not benefit. Now, I don't have time today to talk about that small subset of children that have very hypermutant cancers and the work that has been done at Toronto Sick Kids with Uri Tabori and his colleagues. Their immune checkpoint inhibition with nivolumab seems to have activity, which is really remarkable because these children with mismatch repair deficiencies have a very poor response to standard therapies. And we're conducting a trial in the Pediatric Cancer Immunotherapy Trials Network looking at patients with sporadic pediatric solid tumors who have hypermutant tumors, and we're defining that as more than 10 mutations per megabase. And it's possible if we select those patients that we might be able to see responses. But if you look at the big picture in pediatrics, what you're really looking at here is the difference between patients who have these high mutational burden cancers, and these are largely adult cancers like melanoma, like lung cancer or head and neck, versus those that are more genetically quiet. And it's those up here that respond to the immune checkpoint inhibition, whereas our children's tumors tend to aggregate over here, again, with the exception of the patients with the genetic mismatch repair. And so we really are thinking of pediatric tumors as very different from an immunogenicity standpoint. And so we're now starting to think about immunotherapies based upon what is the underlying immunogenicity of the cancer. If you happen to have an immunogenic cancer that has mutations that the immune system can recognize, then the job of the immunotherapist is simply to amplify the natural immune response. And the prototype in terms of an immune response amplifier are the checkpoint inhibitors, but there are many other things that can also be done to amplify existing immune responses. And, the adult oncology world is very actively seeking to identify the best possible cocktail of immune response amplifiers. And we will certainly learn from them. But for the vast majority of our pediatric cancers, we are sitting in a space that is more in the non-immunogenic cancer space. And for that, if we want to use the immune system, it's my belief that we need to create something that doesn't already exist. We need to use a synthetic immunotherapy. And one could think about monoclonal antibodies as maybe the first synthetic immunotherapies because they don't exist in nature, but you can essentially trick the immune system into recognizing the tumor and then, let's say, attacking it with NK cells or macrophages. Or blinatumomab would be another synthetic immunotherapy where you bring the T cells to the CD19 expressing tumor and then you activate a T cell there. We think the most exciting of the immune response initiators are the chimeric antigen receptors. And just for those who don't think about T cells all day long, this is just primer 101. Mother Nature's T cell is expressing what we call a T cell receptor that signals through several domains, but one of the most important is this zeta chain that gets activated when these T cell receptors recognize a molecule expressed on the MHC on the tumor or the antigen presenting cell. But that's not enough to get the T cell activated. T cells also have to get signal 2, and so this is a layer of regulation or protection to prevent T cells from being too promiscuous. And that's what's required for natural T cells. This is what's absent in most of our children with sporadic tumors. There simply aren't enough of these peptides that are recognized by our children's T cell receptor repertoire. So what some very clever immunologists did back in the late 1980s and early 1990s was they essentially hacked the T cell. They said, all right, we know it can signal if this zeta chain gets activated. How about if we stick an antibody up here or a portion of the antibody that can recognize, let's say, an antigen on the surface of the T cell? And let's just put that co-stimulatory domain right into that initial signal. And so when any given cell surface molecule is identified by this T cell expressing this chimeric antigen receptor, the T cell gets signal 1 and signal 2 and is believed then that it's going after a natural antigen. And so the beauty of this system is that it's modular and that you really can create a CAR T cell that could recognize any antigen for which you can create a binder. And the most common binders are derived from antibodies, but you now can create binders that are non-antibody derived or natural ligands. And the point is that you can make them for hundreds of cell surface antigens that might be overexpressed on your tumor. And so there are numerous of these CAR T cells targeting a variety of antigens that are relevant to pediatric cancer, as you see there. Now, what's all the excitement about? As Alberto alluded to, I've done a lot of immunotherapy trials and vaccines and cytokines and, and K cells. And, if you just activate the immune system, you really have, you can get immune responses that you can measure towards your tumor of interest. But generally, even with a lot of effort, your percentage of your immune cells that are going to recognize your tumor are going to be in the 1% range. If it's 1%, you're really happy. And what I saw when we first undertook CAR T cells back at the NIH, starting in 2011, 2012, is that the quantity and the speed of these CAR T cells was unlike anything I had ever seen before in immunotherapy. So this is flow cytometry, where you're looking at CAR T cells here shown in blue. This is a teenager who had acute lymphoblastic leukemia for which all the standard therapy had failed him. And he had at the time of treatment circulating blasts as well as circulating normal B cells that expressed CD19. And so, of course, at baseline, he had no CAR Ts, but by 10 days after we infused a very small dose of CAR T cells, this is on the range of 50 million CAR T cells. You can see this in the bottom of a 15 ml conical. These cells expand in vivo and ultimately, within 10 days, comprised about 80% of his entire immune repertoire in his body. Coincident with that, it was able to eradicate the circulating and the bone marrow associated normal and malignant B cells. And so it's really the rapidity and the potency of these cells that make them so remarkable for their capacity to treat established cancer. This patient had about 2,000-fold expansion within 10 days. And so the other remarkable thing about CAR T cells is that when you see exciting results that come out of one center, it's exciting, but you start to, you just want to make sure that this is really not something unique about what's happening at that center. And what we saw with the CD19 CARs is this happened at multiple centers with multiple different constructs, complete response rates in children and young adults with fully refractory leukemia, all standard therapies, had complete disappearance rapidly within 28 days. In adult lymphoma, similar response rates, long-term disease control rates. And these were in the context of phase 1 trials, which was really unheard of. And so this led to a rapid evolution of a field of cancer cell therapy, which many investigators have been working on for certainly 50 years, but in many ways it could be encapsulated by the story of Emily Whitehead, who received her CAR T cells. She was the first child to receive these and received them at the Children's Hospital of Philadelphia when she was 6 in 2012. You can see 5 years later, she is now a preteen. She is at the FDA hearing where they decide about approval of these. And remarkably, that little infusion of cells that was infused when she was a young preschool or school-age girl is still circulating in her system 5 years later and surveying for cancer. So this was the first FDA-approved cell therapy for the treatment of cancer. It was the first gene therapy approved in the United States. It was an unusual developmental path because the approval occurred in children prior to adults, really unheard of, but remarkable that we still don't have an FDA-approved CAR for adults with leukemia. First therapy with an outcome-based payment model, and pretty rapidly our community is now moving to look to see whether we might be able to move CAR T cells up earlier. And so now there is a trial underway testing Kymriah in the MRD positive setting in high risk in patients with end consolidation. So this was a watershed moment by all accounts, because when I would go to talk about CAR T cells before the CD19 CAR approval, what you would hear from people, there were a lot of skeptics, and they said things like cell therapy will never work, and even if it did, how could you commercialize it? And blinatumomab does the same thing. Why do you need CAR T cells? Autologous products from cancer patients, it will never work because they're too immunosuppressed. Besides, it will take too long and the disease moves too quick and it's too darn expensive. So this was the type of arguments that I would hear. Now, what I hear is it's too darn expensive. And it is. We are still at a phase where this is highly technologically clunky. It needs to become streamlined. We need to be able to manufacture these cells cheaper, and we need to be able to scale them up for all patients who need it. But as we all know, if a cancer therapy works, the field will find a way to deliver it. So in many ways, the CD19 CAR story has set the stage now for the ability for us to find other therapeutics that could be given perhaps more efficiently or more economically, perhaps off the shelf, allogeneic, or maybe even the big kahuna for solid tumors. So I'm going to go fast about the results in ALL. I've given you the glasses half full perspective there, and it clearly can be seen that way. The downside of the story is that although the response rates have been very, very high, the relapse rates are also high. And we have not yet seen a full plateau in relapse in these patients. We've seen some patients relapse out as far as 2 years. And one of the problem is that most of the follow-up of most of these studies has been short, and many of the patients have gone on to get post-CAR therapy, especially bone marrow transplant. Now, the relapses after CD19 CAR for leukemia come in 2 flavors, CD19 negative and CD19 positive. The CD19 negative relapse has been studied pretty extensively, and it results from selection of cells that are expressing genetic variants of CD19 mutations or enriched for isoforms. Occasionally, there will be a lineage switch, especially in patients with MLL disease. But the thing about CD19 and ALL is it's often binary. You either have it at high levels or it's negative. We'd love to be able to identify these patients up front who are at risk. We don't know what the risk factors are. It may be that a higher tumor burden is a risk factor. It may be that more persistent CARs increase the risk of this. And it may be that children have a higher risk than adults, but I think the data is all still too early. And again, we have no way to identify the risk up front. And the other thing to point out is that CD19 positive relapse is also an important cause of relapse, and in some cases is the majority cause of relapse. And here we know that the risk of that is related to the duration at which the CARs persist. Unlike adults with lymphoma, where it doesn't seem to matter if the CAR disappears after a month, in children with leukemia, you really seem to need these CARs to persist for at least 6 months. And this has been work that came out of Seattle, which is really demonstrating very nicely the increased risk of 19 positive relapse if you lose your CAR before 6 months. And so that has really led to the standard of care evolving, really in the absence of controlled data, but evolving to recommend transplant for patients with CAR persistent less than 6 months. Again, contributing to this post-CAR transplant, leaving us, unable to really understand how prolonged are these durable remissions, what % of patients have durable remissions, and how do we best keep those patients in remission? And this is where you want to step back and think about the various types of CARs. And for children with leukemia, of course, Kymriah is what's approved, and it's a BB CAR. And the BB CARs tend to behave like this. They don't go quite as high, and they last a bit longer. And this seems to be important if you're going to cure childhood leukemia. The 28Z CARs, which is the Yescarta-like, come out very strong out of the gate, and they don't last very long. It doesn't seem to matter for adult lymphoma, but in childhood leukemia, it is likely to mean that you cannot cure a patient with childhood leukemia with a Yescarta CAR because of this short persistence. So at the NCI, before we understood any of this, it was the 28Z CAR that we used to test in pediatric ALL, and we treated 50 subjects after by Trey Lee led the trial, and then Nirali Shah. You can see the ages, children, young adults. The toxicity was significant, but it wasn't something that couldn't be managed. We did see reversible neurotoxicity in about 40%, and it's similar to Kymriah in ALL. And we had a 62% CR. It was a little lower than the Kymriah, but that related more to the fact that we had changed up the preparative regimen at that time before we understood that Cy/Flu was really the better one. And with that, we saw about a 70% response rate. Now, we're in the process of publishing the results of the long-term follow-up of these patients with a median potential follow-up of 4.8 years. And you can see that here you have really good evidence for durable disease control in a very substantial subset. Well, what's the difference between those that recur and those that don't? In this series, it's very clear. If you go on to get an allogeneic transplant after you were put into remission, you do quite well with a very flat tail. In fact, the post-transplant relapse was only 5% at 12 months and 9% at 24 months. And that compares to more than 50% relapse rate after Kymriah at about 12 months. And so the most of the patients that received a transplant in this series had not previously received one. But this is the first data that I'm aware of that says very clearly that in taking patients who were transplant naive to transplant after CAR, it's associated with improved survival. So summary number one here, CD19 CAR for B-cell ALL, it's remarkably high responses in these patients who are refractory to all therapies, and it's changing the outcomes for this patient population. But we still have work to do. We still need to diminish the risk of relapse, and we don't really know what the relapse is with CAR-only therapy. CD19 negative relapse is a big problem, and we need to understand more about the risk factors so that we can preemptively prevent this. The CD19 positive relapse appears to be related to the short-lived CARs, and so anything we can do to prolong the CARs persistence, we think will address that. And this issue of post-CAR transplant, I think, is still one that the field needs to grapple with in a proactive manner. We see that post-CAR transplant, at least in transplant-naive patients, has diminished risk. And I think that while I had hoped, like many of us, that CAR T cells would put transplant out of business for ALL, because we all know that the toxicities of the myeloablative regimens that were given and the graft versus host disease are very substantial. But unfortunately, I just don't see the data as providing clear guidance that we can avoid transplant in many of these patients. Okay, so what about the 19 negative relapse? Well, we think you have to go after other targets. Most of these patients who recur with 19 negative disease retain CD22, as you can see there, similar to the CD19 positive population. And my lab had developed the CD22 CAR back in 2013 that we took to the clinic. And these are the results with 58 children, young adults treated with the CD22 CAR. 88% had received previous CD19 targeted therapy. Most had received CAR, but some had received blinatumomab. And almost 60% were 19 negative or dim. And you can see that this was also a very active CAR, especially once we got to the active dose. And now with about 50 patients treated, 58, I guess, we have a 70% CR rate, and 80% of those were MRD negative. So the FDA has awarded this therapy a breakthrough designation. And we think that this is, something that really we'd like to see into the commercial space so that we could have this as another option for our patients. So that's the good news. But like the 19 CAR, we do see a high relapse rate after the 22 CAR. And unlike the 19 CAR, where we sometimes see complete loss of the antigen, with 22, we more likely see downregulation of the antigen. And you can see here the flow cytometry of 22 pre-treatment compared to a typical patient at relapse where you get this smear. And at first we thought, well, is that, downregulation enough to really escape the CAR? We didn't really understand how much target was needed. And then we ended up spending a lot of time on this. And it's very clear from our data that you really need high levels of a target for a CAR to be fully and appropriately activated. This is some of that data with the 22 target. Here you have 10,000 molecules per cell, 4,000 and 2,000 molecules per cell. We've created these lines to measure this. And you can see the difference in cytokine production related to the CAR. And then if you administer, in this case, a cell line with 2,000 molecules versus one with 4,000, that makes the difference between being able to control the leukemia in these mice versus not being able to control the leukemia. So this issue of antigen density and CAR functionality is one that we've spent a lot of time on in the lab, and it's really been led by Robbie Maisner, a very talented fellow in the lab who is now an assistant professor at Stanford. He's made targets with all kinds of CD19 levels. You can see there spanning the gamut, multi-logs. And he shows that also for the CD19 CAR, the ability to kill can be demonstrated very clearly related to differences in antigen density, the ability to proliferate, and the ability to make IL-2. Now, what Robbie wanted to do then was to try to understand through engineering how we might be able to overcome this. And it gets a little wonky if you aren't a CAR person, so I'm going to go through quickly since this is published. But basically, he first wanted to know whether 41BB and 28 CARs differed. And we know that a CD28 CAR gives you a stronger signal than a BB CAR. Here's your phospho-CD3 zeta and your phospho-ERK. And we know that the CD28 CAR makes more cytokine than a 41BB CAR. And so now what we're doing is we're going down on the number of molecules or going down on the level of activation with a plate-bound antibody. And you can see that 28 can fire at lower levels of antigen. And this is evidence in a killing assay showing how much better 28 is against a CD19 low leukemia and in vivo. Here's another antigen, HER2, where you see the same thing, that the CD28 is better able to control a HER2 antigen that is expressed at lower levels than BB. So whereas BB has become sort of the favorite in the field of pediatrics, in part because of this requirement for persistence for ALL, and it does persist better, we are likely to be paying a price on antigen density. Now, what Robbie wanted to know was it really the strength of signal? So what he did here is he put two zetas in. He took a BB and he double zetaed it, and he gave it a stronger signal. And when he did that, he was actually able to see better proliferation with low antigen density. And you can see in vivo better control with a double zeta compared to the single zeta. In this case, it was similar to what you saw with 28, and you were able to see retained persistence. So now we're trying to take the best part of the BB, the persistence, and the best part of the 28, the power, and trying to merge them. And that's the beauty of the CAR engineering. So the other thing that Robbie discovered here was that the transmembrane and hinge domain played an important role in the ability to recognize antigen low. So again, for the aficionados, these different CARs that are out there have different hinge and transmembrane domains. And what he discovered, and now this is with a B7H3 CAR, which we hope to bring into the clinic for childhood solid tumors, you can see that changing the BB domain, the CD8 transmembrane domain, which is typically found in the BB CARs, to a 28, really renders this B7H3 CAR a lot better against low antigen density. And we've done some of these super resolution microscopies to understand this better. Here we're looking at ZAP70 that is now labeled with GFP, and ZAP70 is one of the upstream signal mediators for the T-cell receptor. And we know that it's needed at the synapse in order to get the signal to fire. And you can see that at low antigen density, look how much more ZAP70 is at the synapse compared to low antigen density. And this is just shown mathematically. What we're doing now is we're getting better at engineering. I showed you the data with 22 and with 19. So the question is, maybe we should just come back with a double CAR. Again, getting at the potential for better engineering of CAR T cells. So we could do that by co-administering 2 pots of cells. We can co-express, or we can make one bivalent vector. And at Stanford, we launched the trial with this bivalent vector, which we showed could recognize and kill targets with either 19 or 22 or both. And so we've opened 2 trials of this double CAR at Stanford. You can see that it is well tolerated. We've done this in adults and in children, and we don't see any increase in toxicity with the bispecific CAR. And so what we're doing now in acute lymphoblastic leukemia across the age spectrum, really conducting trials in adults and children using a team that is working very closely. You can see we've enrolled folks from ages 2 to 69 on a trial of this double CAR. It's harmonized so that the safety data from the adults informs the pediatric trial. And this CAR induces an 88% MRD negative CR. So that's great. But what about the relapse rate? Well, just like all the other CARs for ALL, we still see a significant relapse rate, and we are still seeing CD19 negative relapses. So while we can create a bispecific CAR and it shows activity and good safety, we still haven't fully harnessed the power of the CD22 CAR. So here I want to summarize and make the point that tumor heterogeneity with selection of antigen loss or antigen low variants, it's a major cause of resistance to CAR T cells. And we can create multi-specific CARs to address this, but we still don't know fully how to create those. The engineering still needs to be optimized. We also know that CAR T cells need high antigen density for optimal performance. And this is different from a natural T cell receptor. And while it provides challenges for antigen escape, it also provides opportunity, because it means that we can now begin to tune the antigen density threshold based upon the given target. We can make a CAR that can go very low on a target, like we may want to for a B cell antigen. Or we can make a CAR that would ignore antigen low, like we might want to for something like HER2. So this is all about engineering intelligent design CARs. And this is why there remains so much enthusiasm in this field, multi-specific CARs and tuned CARs, because these are the kind of tools that we're going to need in our toolbox if we're going to successfully go after solid tumors. Because unlike B cells, where the antigens are very clear and they're homogeneous, and we can allow normal tissue toxicity, of course, it's all much more complicated in the solid tumor CARs. And so far, there really hasn't been convincing evidence of reproducible activity in solid tumors. So why do I remain optimistic? Well, I think that we understand what the problems are: tumor heterogeneity, challenges with trafficking, and impaired T cell function, and we have tools in our toolbox to go after them. I want to talk about brain tumors. Diffuse intrinsic pontine glioma, of course, a devastating pediatric solid tumor. The ones that have the H3 K27M mutation are lethal in 100% of patients. And Michelle Mange has been a pioneer in progressing our understanding of DIPG, and she did a very simple unbiased screen of what's on the surface of these cells. And the top hit of all the things that she put in to her screen was GD2, of course, an old friend to most of us. Here's GD2 on the DIPG cell lines. You can see that those with the H3K27M mutation express high homogeneous levels of GD2, as opposed to those with the H3 wild type do not. So the surfaceome reflects the tumor biology. Michelle has an elegant orthotopic xenograft model in neonatal mice where we now administered the GD2 CAR. We saw full clearance with one infusion intravenously of our GD2 CAR T cells. You can see complete absence there compared to infiltrating disease with our control CD19 CAR in this setting. Now, this was curative in these patients, in these mice. We did not see relapses, although we did lose a few animals early, and those animals died due to hydrocephalus. Here's a picture of the hydrocephalus in some of the animals who died early after the GD2 CAR. This was related to tumor location and tumor swelling. We saw no evidence for neuronal toxicity, even though we're well aware that GD2 is expressed on neural tissue, it's expressed at low levels. We saw no evidence for CAR killing of nerve tissues, and in fact, in the animals for which all the tumors cleared, what you were left with was normal-looking neural tissue, and of course, GD2 is the same in mice and humans, and so our CAR crosses. So this was published in 2018, and in June of 2020, we launched a first-in-human, first-in-child trial of autologous GD2 CAR T cells for H3K27M, DIPG at Stanford. And the eligibility is age 2 to 30. These patients are eligible if they have H3K27M DMGs. They have to have a biopsy to confirm this, either in the brainstem, the pons, or the spinal cord. We are not enrolling thalamics because of the concerns for tumor swelling. We are not requiring recurrence. These patients, because of the very severe outcomes and because of the very short post-progression survival, we've decided to allow enrollment after primary therapy, which is focal radiotherapy. There are washout periods there and performance status. All of our patients are having an Ommaya catheter placed because we really want to monitor for this problem of increased intracranial pressure and to be able to treat it emergently by removing a CSF if need be. And this also is now providing us with an unparalleled access to CSF for correlative studies. The treatment plan is pretty straightforward for CAR T, apheresis and CAR T cell manufacturing, all told about 14 days. During that time, patients are getting their Ommayas placed. Then they get a lymphodepleting chemo regimen, Cy/Flu, very similar to the leukemia regimens. They get seizure prophylaxis. We're doing a dose escalation, 1 million, 3 million, 10 million per kilo. And of course, they're monitored very closely for what we think are 3 potential distinct toxicities. Cytokine release syndrome, which of course the CAR T cell field knows very well and understands. Immune effector cell acute neurotoxicity, or ICANS, which we see, but we don't understand very well. It has been most notable after CD19 CAR. In fact, we don't see it much after CD22 CAR. We think it's related mainly to cytokine mediated inflammation in the brain, although there still remains the possibility that there are CD19 cells in the brain. And we think there's going to be a third type of neurotoxicity that we're going to see that we've coined tumor inflammation associated neurotoxicity, essentially due to swelling of the tumor in the closed space of the CNS. Here are some early correlative studies on our first patient treated. You can see that very early in the CSF, after intravenous infusion, we start to see acquisition of inflammatory cytokines in the CSF. This is associated with an increase in cell numbers in the CSF, most of which appear to be monocytes and microglia, although there are some lymphocytes in the CSF. This patient ended up getting steroids for CRS and some neurotoxicity, and it was interesting after the steroids, the pattern of the cytokines changed. Whether that was due to the steroids or simply due to the timing, we don't know. Here's the second patient that was enrolled. This patient ended up not being treated on trial because she progressed very rapidly to paralysis, and therefore we couldn't assess toxicity. This is a spinal glioma. And so we've treated her on a compassionate study, a compassionate single protocol. But we were excited to see here what looks like shrinkage of her spinal cord tumor by day 31 after the GD2 CAR. So it's still very early. We think that, the surfaceome of human cancers, we don't really know what's on most of our tumors. And there are, GD2's been, hiding in plain sight on DIPGs for quite some time. And this also illustrates how tumor biology drives cell surface phenotype. These H3K27M diffuse midline gliomas have ultra-high levels of GD2. And in a murine model, we were able to show eradication of the tumor without evidence for on-target neurotoxicity. And we also know from several trials of GD2 CAR that there really hasn't been any evidence for neurotoxicity, peripheral or central, consistent with the therapeutic window. And even in the case of some patients now with GD2 CAR are seeing responses. So this clinical trial we've launched, we're excited about it. We think we see some interesting results, but it's still quite early. I'm going to run out of time, I guess. So let me just do one more story here. Again, harping on this idea that we need to know more about the surfaceome of our patients' tumors so we can develop immunotherapies. Comprehensive profiling of the surfaceome in neuroblastoma has been led by John Maris's group. He identified GPC2 as well as other targets. Michelle Sadelaine looking at surfaceome in AML. This was our work looking at the surfaceome in Ewing's. And we know that GD2 is one, but GPC2, PAPA, B7H3, or others for some of the most difficult to treat tumors express high levels. We've now engineered a GPC2 CAR that requires next generation engineering with alteration of the hinge transmembrane domain that I talked to you about. That made all the difference in this GPC2 CAR because GPC2 is expressed at low levels. But it's not expressed at all in normal tissue. And with this next generation engineering, we have very impressive activity in preclinical models. And B7H3 we think is a great target as well. We recently published a paper showing that it's highly overexpressed in atypical teratoid rhabdoid tumor. B7H3 is highly expressed in fetal brain, but is silenced right after birth and remains silenced in the brain. And what we believe is that ATRT is really a developmental disease that in many ways mimics fetal brain. Look at B7H3 expression on fetal brain compared to pediatric brain, and here it is in ATRT. So we think that this could be a very good target for ATRT. And one of the things about CNS tumors is that they are relatively regional diseases. So we can inject these CAR T cells actually into the brain because peripheral disease is really not our major problem. And we had really followed the work from City of Hope showing that brain infusion was more potent. So we did it ourselves in this ATRT model. And indeed, what we saw, if we gave the CAR T cells into the brain, we could cure all the animals with 1 million CAR T cells. Whereas 1 million CAR T cells had no effect. We had to go to 10 million if we gave them intravenously. And the intracerebroventricular trafficking results in more rapid trafficking into tumor and lower systemic cytokine levels. So we think there will be less systemic inflammation and similar persistence in the brain. That was remarkable. I expected them to just, die because I didn't think that, lymphocytes lived in the brain for a long time. But here they are looking persistent in the brain, similar to what we saw with IV. And when we gave the intracerebroventricular delivery, remarkably, we see these T cells come to the periphery. So even though we're giving tenfold less, they actually traffic into the periphery at similar levels to IV delivery, and they protect against a challenge put on the flank of the animal. So here is an animal that's challenged now with a B7H3 tumor on the flank, and you can see that even if you gave the CAR T cells intracerebrally, they also protect against both, intracranial rechallenge, and they protect against flank rechallenge. So I'm going to stop here. Again, make the case that surfaceome profiling, we need our tumor biologists to do this work for us. We think you'll identify some novel targets that may be important for biology and can certainly give our immunotherapists targets to go after. And we don't think the target has to be entirely clean to go after it. We have ways to now regulate our CAR T cells so that we can go after some of these targets with low-level expression on normal tissues. Because these pediatric solid tumors are disorders of development, they may be expressing a lot of these fetal molecules that are silenced at birth or later in life. And this could be a specific opportunity for our pediatric patients. Brain tumors are largely regional disease, and it may be an opportunity for cell therapies because of the ability to deliver these cell therapies regionally into the CSF. It looks like it really is more potent, less toxic, and promising. And so, of course, we're thinking about that with regard to our GD2 CAR with DIPG. So I'm going to stop there. Just want to get to my acknowledgement slide. Lots and lots of people have worked on this. This clinical work, of course, is the work of many, many investigators. I mentioned the work of Joanna Theravath with the ATRT, Robbie Meisner with the low antigen density, Sabine Heitzenetter, who is working on the GPC2 CARs, and of course, Michelle Mange, which has been a great, she's been a fantastic collaborator on the DIPG. So I'll stop there and take questions.
That was fantastic, Crystal. Thank you very much. And we have several questions from the audience. One of the questions is, the other side of the loss of antigen density equation is the loss of CAR density on T cells. Have you observed any change in CAR density after treatment, or perhaps between patient products after manufacturing?
Yeah, thank you for asking that. We actually got into this business when we started to try to make an ALK CAR. And we published this in Molecular Therapy in 2017. And this ALK CAR never worked very well. We like to understand when they fail. And the problem with the ALK CAR, first and foremost, is we never could get it to express very well. And so that was our first insight into this equation, that, the ability to find a lot of targets or to fire at the synapse is related to CAR density, CAR affinity, and antigen density. And so one way to overcome it is to overexpress your CAR at higher levels. The problem with that is that when we express CARs that are single chain FV based at very high levels, we tend to see this tonic signaling. And the tonic signaling, I didn't get time to talk about it today because I ran out of time, but drives these CARs to exhaustion. So it is our feeling that there is a bit of a zero-sum game there of increasing your CAR density too high, because as the cells get exhausted, then they also require higher antigen density. But certainly the CAR density matters. We agree.
There's another question about tumor heterogeneity, that it's a large problem in solid tumors. Is this the case for pediatric solid tumors as well? And can you comment on inroads made in multi-targeted CAR strategies for pediatric solid tumors?
Yeah, I mean, this is any oncologist who thinks they're going to cure a cancer with one target is, likely kidding themselves. I mean, even, the CD19 CAR is kind of an exception. And frankly, the immune checkpoint data, right? Curing metastatic patients with one target. This is really, I think, why it was so seminal. But chances are those are the exceptions to the rule because of the fundamental issue of heterogeneity. So we are fully expecting that multi-specific CARs are going to be needed for solid tumors. This is one of the reasons we put so much energy into understanding how to make a multi-specific CAR in leukemia, where we have so much understanding of the system and we can learn very readily why our CAR T cells fail. So yes, we will need multi-specific CARs. And, you know, our 1922, it's unfortunate that we lost the potency on 22, but I think we understand a lot more about how to do this. Frankly, our current idea is that co-transduction may be the best way because we think that the bivalents are very tricky, and we think that the bicistronics you lose on CAR density, as we were just talking about. But these are all engineering challenges that I think, you know, we can get there. There's more work to do, but there's no fundamental reason we can't make highly potent, you know, quad-specific CARs, for instance. We've made quads against GBMs in our lab, and, you know, it's quite doable.
And this leads me to the next two questions. How far away you think we are from targeting 3, 4, 5 antigens at a time? And do you have any suggestions or ideas as how we can lower the cost of engineering?
Because those are interesting if you put them in the same question. Yeah, we have a bell and whistle problem in this field because, you know, the second half of what I ran out of time for was the whole exhaustion resistance world. So we want multi-specificity. We want increased persistence, and we want, you know, powerful T cells. And, you know, we have ways to engineer for each of these things, but the more you put into a cell, the more complicated it gets. And again, I think in a way the science has advanced beyond our ability to do GMP manufacturing for these, what I call the bells and whistles. And so our manufacturing science has to catch up, but all of that costs money. And, you know, we're paying $473,000, $75,000 for a CAR that is quite simple. And so I'm very hopeful that this will be like a Moore's Law kind of a thing, that the technology in the cell and gene manufacturing space will pull the costs down, especially as more competitors come into the space and, there's more competition. So, but all of that's going to take time. I mean, I'm hopeful, but it's not going to happen tomorrow.
I have one more question, and that is the challenges to design universal CAR T cell therapy.
Now, when you see universal, so you're not talking about off the shelf. You're talking about a CAR T cell platform where you can change the antigen midstream. Is that what you're?
So the specific question says that CAR T cell therapy is very specific for an individual, and an individual T cell is modified. What are the challenges to design universal CAR T cells? So I think he's talking about off-the-shelf CAR T cells. That's what I get out of this.
Got it. Yeah. These are going to come down the pike. It's mostly, happening in industry because I guess, the arguments for an off-the-shelf CAR, I think the most compelling arguments are cost. Because if you could create a bank, cost and time, you would make everything so much easier. The patient wouldn't have to go through apheresis, the time would be cut short, and all of that. And because of that, and there's lots of money to be made, and so this is something that industry is very, very motivated to do. And it dovetails very nicely with lots of advances in CRISPR and gene editing, as well as advances in iPSCs and stem cell biology. So we're going to see off-the-shelf CARs. Of course, Allogene already select this. They already have these in the clinic. We haven't solved the immune rejection problem. And for something like lymphoma, where you don't need these things to live very long, it might be all right to have a CAR that doesn't last very long. But for childhood ALL, where you need this thing to hang around for 6 months or more, I think we're a ways off from having an off-the-shelf that is that persistent because of the immune rejection challenge. The other thing I worry about is, of course, in our pediatric diseases, we don't have the big markets. And as I mentioned, I think the biggest incentive for the off-the-shelf is economic for the private sector. And so they're going to go after the big markets for this. Whether they're going to spend all of the money it would take to make a perfect off the shelf for DIPG, I kind of doubt it. And so I wonder if that might remain in our academic sphere, perhaps with distributed manufacturing. I think that those are the kind of things that I envision for the future of some of our rare diseases.
Thank you very much. It is the top of the hour, so I'd like to thank Dr. Mackel for her exceptional talk and to close the official event, and also to invite all of who are interested to stay on for a continued discussion of any further questions you may have. Thank you all for coming, and I encourage you to visit the website and mark your calendars for other upcoming talks, including Rick Young and Isaac Klein from MIT and Dana-Farber Cancer Institute on October 22nd, who will be speaking on partitioning of cancer therapeutics in nuclear condensates. Thank you very much. So I don't see any additional questions, but actually I had a question for you, Crystal. So
Yeah, sure.
is there an optimal platform to identify antigens, and how do you credential those antigens? How did you find out that GPC2 was the right one, or B7H3 versus another one? Is it the level of expression? Is it the expression of this antigen throughout the body to be sure that you don't mess up the liver or the skin? And how compelling does the data have to be to say this is the right antigen?
Yeah, I think, first of all, it's hard work. Most of us, the immunotherapists, we kind of do it, but we do it on the side. And I really, when I give these talks, I really want, our tumor biologists to take this on. Because I think some of these antigens that they find actually are important for the pathobiology. GPC2 turns out to be downstream of MYC and overexpressed in the stem cell compartment, all of that. Because I think to find a good antigen, you need to think about it biologically too, right? Because something that the tumor needs is a lot more compelling than something that just happens to be there. It's a little naive. Most things aren't just happen to be there. But if you have something that really is integral to the onc, so I think understanding the biology of the target is really important. There are quite a few algorithms now that allow you to start with transcriptome RNA and simply, use your cell surface filters, which are now, again, readily available. And then you put it through an algorithm, and you kind of have to decide, what are you looking for? Are you looking for an antigen that is absent from normal tissues? That's like GPC2. It's very clean. That antigen is expressed at what I would call moderate levels. And so it's a clean antigen, and the ones that are expressed that are clean tend to be expressed at moderate levels. And for that, you need a CAR that can go down low. But GD2 is the other paradigm, where you have something that's very high, but it's expressed on normal tissue at low levels. There's still a delta there. And it is my belief that you can go after the latter variety, but you need to do it with a CAR for which you have some safety switches incorporated. So there are two classes, those that are very highly expressed and expressed at low levels on normal tissues, and those that are absent on normal tissues and expressed at moderate levels. It's very hard to find one that is really high in the tumor and completely absent. And then, one of the things that I've been very excited about, there was a paper that just came out from Stanford where they used single cell RNA-seq data, because one of the challenges of credentialing an antigen is if you just look at bulk RNA-seq, so we just did this with something called CD93 on AML. And it looked very clean. It looked like it was expressed on hematopoietic cells only. But then we did the IHC and it was on endothelium. And the bulk RNA-seq really doesn't show that, because if you just take RNA-seq from tissue, endothelium is only a small portion of that. But if you do single cell RNA-seq, it's staring you right in the face. And that's how this group at Stanford identified that CD19 is expressed on the mural cells of CNS, vasculature vessels. They're not expressed on mural cells anywhere else. So I think single cell RNA-seq is very helpful. And the other point to make is, when you start with a transcriptome, what you find are proteins that are overexpressed. but you would never find GD2. And you wouldn't find differentially glycosylated markers and stuff like that. So the other thing is, if you want to do this seriously, maybe you should start from a proteome. And this is why we need those tumor biologists, because they're, have all these techniques and skills, and I think can really help us. What we need is a comprehensive profile of what is on the surface of our pediatric solid tumors. What's there?
Thank you. There's another question. When looking at multiple targeting with CARs, it seems that the bivalent CARs or dual expressors on the T cells are favored. What are the limitations of administering 2, 3, or 4 CAR T cell types?
Oh, yeah. Okay, they don't work very well. I have to tell you, when you co-infuse, what we have seen, and this is in mouse models, so you can argue with it, but there's a competition. There's an intense competition for limiting resources in vivo, and the quickest one out of the gate wins. So like one thing you might think about doing is, why don't we use 1928Z and 19BB? You get the strong power of the 28 quickly, and then you get the persistence of the BB. If you do that, you never find the BBs because the 28 take up all the space. If you administer 19 and 22 together, same thing happens. 19 crowds out 22 because 22 is not quite as powerful and the antigen density isn't quite as high. So it's the idea that when you give 2 pots of cells, they're both equally advantaged. I don't think it's true most of the time. And besides that, that's the most expensive and the most time consuming, the most resource intensive way of doing it. So I'm really not in favor of it. I know Penn is doing it now with the 1922. I think that, we can do so much better than that.
So I think this is all we have. And again, thank you, Crystal. I know that your schedule is super busy. Just thank you for taking the time to doing this. We truly appreciate it.
Good. All right. Thank you.
I look forward to seeing you soon. Thank you so much. Thank you.
All right. Thanks so much. Bye.
Thank you. Bye-bye.